Okay. Welcome to the Ignited Minds podcast. We're thrilled to present another episode packed with stimulating insights and discussions. Our special guest today is the esteemed Dr. Aksoy. So, can you share a bit about your background and any current work that you're working on?
Sure. So thanks for inviting me to your podcast. So my name is Doruk Aksoy, and I'm working as a postdoctoral scholar at University of California, Irvine, as part of Materials Research Science and Engineering Centers, so MERSEC. So my research focuses on computational material science, which includes materials such as metals and high entropy alloys. Utilize techniques such as atomistic modeling and artificial intelligence for the microstructural design of alloys.
Hmm. So, when I was looking through your research, I noticed that you use atomistic modeling and simulations in your research. How did these computational tools help you kind of get different insights into the behavior of materials and uh, make it easier to kind of discover new materials?
So in material science, research is typically conducted through three distinct but interconnected approaches. So these are theory, experiment, and simulation. So these theoretical frameworks, they describe the fundamental principles, and they also lay the groundwork for making predictions, and also for computational simulations. So on the other hand, experiments give us invaluable data on material properties, as well as enabling investigations through imaging and characterization techniques. However, these experiments often require extensive time and resources, and so some conditions like the environment inside a nuclear reactor are simply too extreme to make these direct experimentations. So that's where the simulations come in. You can think of them as virtual experiments inside of a computer. So they model material behavior, offering insights, especially when real-world tests are infeasible. So these simulations are, can span multiple scales. So they could be from the subatomic scale, where you have these quantum interactions, to the macroscopic level that can access higher scales and longer simulation times. So my focus is mostly on the atomic scale behavior. So at the atomic scale, many microscopic properties like a metal strength, for example, or ductility are influenced by atomic level factors. So
Okay.
these factors could be like dislocations and grain boundaries. So simulations offer a microscopic view to explore these key details, which in turn shapes how these materials are processed and synthesized. So my particular area of expertise is molecular dynamics simulations. So in this approach, we model atoms as point masses or like hard spheres. So we aggregate all these different subatomic particles into that hard sphere, and then we use Newtonian physics um, to identify the movement of these particles. So what's exciting about these simulations is that it allows us to rapidly search through an array of alloys, for example, so we could understand how different elements or doping levels can modify a material's behavior. So they also offer insights into mechanisms like diffusion, like phase transition, and defect formation.
So, are there any specific artificial intelligence or simulations that kind of have helped you recently in your work?
Absolutely. So AI has become an invaluable asset in tackling complex challenges within material science. So one of its primary strengths is its ability to identify patterns in complex cases and huge data sets. So it's an excellent complementary method to traditional theory and simulations.
Hmm.
So going back to materials discovery, AI allows us to analyze vast data sets to identify promising material candidates based on desired properties. So machine learning models are particularly useful here. So they could predict material properties from just their structure and composition. So beyond that, AI just is really good in uncovering hidden patterns in complex data. So it could identify like subtle mechanisms, such as phase transitions or defect formations, so which are often difficult to identify through conventional analysis. So atomistic simulations are really powerful for modeling material behavior, but they are computationally intensive. So one breakthrough with AI in my research is to extend these boundaries of these simulations. So we are focusing on high entropy alloys, which is a very interesting but complex class of materials. It has multiple alloying elements. So the computational challenge here is, understanding how these elements interact, especially.
So you mentioned during the second question that you use artificial intelligence and material science in a very interdisciplinary way and kind of utilize all of these different types of computational modeling and simulations to overall address one main challenge. So how do you think adding on so many different fields can help the intersection of uh, can help like so many different fields work together and just overall be more efficient?
Yeah, so great question. So I guess to best illustrate this, we can talk about a concrete example. So in material science, electron microscopy is a technique that provides us with high-resolution images of specimens. So unlike optical microscopes, which use light, electron microscopes use electron beams to generate these images. So the captured images will often have hundreds of grain boundaries, which are essentially two-dimensional defects that interface two grains. So identifying these grains manually is time-consuming, and also it's prone to human error. So this is where AI is especially useful. Specifically, we employ a technique called computer vision, a branch of AI dedicated to image processing, so that we can automatically identify these grains. So we achieve this by using the theory of how our human perception works and transforming this understanding into algorithms that allow AI to efficiently complete this task. So the result is impressive. The tasks that could take a human hours to complete are finished by AI within like milliseconds. So in addition to that, the AI identifies most grains with high accuracy. So yeah, this example, I guess, highlights the incredible potential of merging these, material science and AI tools. The application of this approach is not just about speeding up research, but it opens up, new avenues for tackling complex real-world problems in material science.
So with artificial intelligence, everyone kind of starts at a baseline for where artificial intelligence can kind of help in different fields. And the more data you give it and the more developed this AI becomes, the more useful it can be for your field. So how have you been kind of developing artificial intelligence to be more useful for your own uses?
So one of the most important problems right now in artificial intelligence methods, employing these methods, is to obtain different data. So not only the quantity, but the quality of the data also matters. So you have to have this high quality data that you can feed into these neural networks so that you'll get a good result. So in material science, this is sometimes hard because you have these experiments that are time intensive, requires human labor, and then in the end you won't get much data that you can work with for your neural networks. So it's really important to identify these shortcomings of machine learning methods. There are some ways to tackle this problem. You can use like synthetic data, for example, or you can always try to get more data. But in the end, it's more about getting that quality data, which is something that atomistic simulations and other methods are really helpful in, so that you could have, you could gather all that data, so that you'll know that you will have this good result in the end.
So the more data you're collecting is, as you mentioned, it just helps artificial intelligence be that much more efficient for your own work. And
Yep.
Currently, artificial intelligence is mainly being used for pointing you in the right direction, as opposed to giving like a concrete solution or something similar to that. So, what are your thoughts on this?
Yeah, so when using AI, it's really important to know its limitations, which are, at the current time, it's about a data method. So it depends on the data, but it generally doesn't know anything about the underlying physics, for example, which is really important in material science. So it can give you unphysical results. So if you use an AI tool and then give it bad data and then don't actually know what you're doing, then it's a high probability that you will get some unphysical results, meaning that you can't have a material system like that, or you can't have material behavior like that. So it's really important to first of all know your field, know the fundamental physics behind it, so that you can use these tools to basically augment your research, not replace it.